Hello. This training will be on Transmission Control Protocol, TCP. Today we will cover learning objectives, why do you need it, exercises, learning verification, and summary. Learning objectives. Now, what does it mean? So, the learning objectives, if you're familiar with the training or if this is your first session, I'll just state that the learning objectives specify questions that you will be able to answer as a result of receiving the training today. First, what does it mean when one says that IP encapsulates TCP? What are the 7 layers of the OSI model? What is the TCP three-way handshake? Can an application work if the TCP three-way handshake fails? What do SYN and ACK mean? What are sequence numbers? What do consecutive SYN without a SYN ACK represent? What is MSS? What can be indicated by an MSS less than 1460? Why do you need it? Okay, so quoting RFC 793, the Transmission Control Protocol, TCP, is intended for use as a highly reliable host-to-host protocol between host and packet-switched computer communication networks and in interconnected systems of such networks. So in layman's version, that means TCP can detect whether or not the other system is responding. TCP allows for the transmission of data in small pieces that can be later reassembled into the original data. It also means TCP will work over the internet. I don't know why, but for some reason haughtiness just sounds like a British accent. I have no idea. Now, exercise 1, understanding protocol encapsulation. What does this picture show? Data encapsulation. So this picture here, you see this picture and you may not quite know what it means. But actually throughout this series of classes, we've been covering content related to this picture. So this picture actually shows how each successive layer adds its additional headers. So this is showing data encapsulation. As you see, this is, and I will go through that. So at layers 7, 6, and 5, you have the data that's generated by an application. Now, as we know, on its own, this data really can't get anywhere else. But we can add additional headers to get data from place to place. In this case, the layer 4 protocol will add source and destination ports to this data. Thus, if we're using TCP at the moment, TCP would encapsulate the data. It covers it up. Now, next, the Internet Protocol, IP, would add source and destination IP addresses. So we can say that IP encapsulates layer 4. Next, at layer 2, the source and destination MAC addresses enter the picture, and the ether field is added. Also, there is a frame check sequence that is added. This is used to determine if there was an error in the transmission. Only in the transmission of the frame itself, not necessarily whether or not there was an error in these higher layers, just an error in transmitting what it received at layer 2. Now, finally, all of this gets encoded into bits. These bits are sent out across the wire, and these get to the other system, and the other system will do everything in reverse. So it'll take these bits, see what the frame is, it'll receive that frame that was translated into bits at layer 2, then it'll it'll receive it, then strip off this, and then it'll look at the source and destination IP, and then strip off what until it eventually gets this juicy data inside the package, because that's the important part, and that's what you really want to send to this data. Everything else is just headers, right? Except for this guy. Now, exercise 2, understanding protocol encapsulation. So what do we mean when one says that Internet Protocol IP encapsulates Transmission Control Protocol? Well, the answer is on the next slide, though we probably covered it already. So if we look closely, it basically means that TCP can be contained within an IP packet. As you can see, all of this information here at layer 4 segment, this is the layer at which TCP operates. And you can see this information for TCP will be encapsulated within IP here. Exercise 3, understanding protocol encapsulation. Now, an obvious question is, why is encapsulation covered so late in the course? Because by now we're deep into the course. You know, we've done several lessons, and now we're finally getting into encapsulation. Well, actually, there was a concern that students would be exposed to it before they were ready. But now the students have an idea about binary, so they know what bits are. They have an idea about switches, so these source and destination MAC addresses make sense now. They have an idea about Ethernet. They have an idea about Internet Protocol. They have an idea, and now we're introducing TCP. So at this point, hey, we'll just introduce encapsulation, versus if we introduce encapsulation or these different models in the beginning, it wouldn't make much sense to you because you wouldn't understand what these actual component pieces even meant. Now, what about the OSI model? Good question. What about it? Well, the OSI model isn't covered in this course. The intent is to arm the student with practical knowledge that would be immediately useful. Okay, great. But how can I remember the OSI model? I mean, because a lot of students have to memorize this for introductory networking and computing courses. So from that perspective, it's immediately useful to them. So here, I have this image of the OSI model showing the 7 layers of the OSI model. OSI meaning Open Systems Interconnect Model, which is a model for network communication where different things take place at different discrete layers. Note that this is a model and not necessarily a requirement. Now, so how can I remember the OSI model? So here's a few acronyms you can use. All people seem to need data processing, or another common one is please do not take sausage pizza away. Please do not take sausage pizza away. And here's one I thought up. All people should try networking data packets. Everyone should try it. Networking is fun. It's rewarding. And did I already say it's fun? Networking is fun. Next, exercise 6 of 12, TCP handshake. What is going on here? So I see client, SYN, server, SYN, ACK, client, ACK. And maybe I don't know what this means. So what's going on here? Well, actually, this is the TCP handshake, which is, a clue for a lot of these questions is in the title of the slide. So the TCP handshake is the sequence of initial 3 packets that establishes a TCP session. And once the handshake completes, the session can then be used for an application. If the handshake fails to complete, the application will not work. So we don't say SYN, SYN, ACK, and ACK. We actually say SYN, SYN, ACK, ACK. That's how we usually say it in the industry. Now, okay, but what does a TCP handshake look like? Because seeing those words doesn't mean much to you. So let's get a little deeper. Okay, so here we have a little screenshot taken from Wireshark here in the bottom. And so this is what a handshake looks like. The client, in this case, this is the client, sets the SYN flag. and then the server will set the SYN and the ACK flag, and then the client will set the ACK flag. So this gives you your SYN ACK, and your ACK. Notice the protocol being identified here is TCP, using these SYN and ACK flags. You see the source and the source port. You see the destination and the destination port. And then when the destination responds, it is a source sending back to the originating client. The way you can tell the difference between who's the client and who's the server is the client starts sending to the server with the initial SYN. The server would respond to the client with the SYN ACK. Then the client would send to the server with an ACK. And that's how you can figure out who's the client and who's the server for a particular TCP session. If you have access to those first three packets, the SYN ACK, and the ACK, it'll be very easy. In fact, if you even have the initial SYN, you would know, because obviously the client is sending the initial SYN to the server. Now, maybe we weren't clear though. What does SYN and ACK mean? Because we're talking about these flags, but we really haven't explained what they mean yet. And so let's not confuse ourselves here. What do these mean? Okay, so SYN, SYN, is actually short for synchronized sequence numbers. And it is seen on initial packets from a host, from this client sent to a server, and it is also seen on the initial packet from the server going back to the client. Now the acknowledgement, it signals to the other side what has not yet been received, interestingly enough. Now, okay, so what are sequence numbers? Okay, so as you can see here, this actually shows sequence numbers here, and the sequence numbers appear to be going up. They appear to be incrementing. Interesting. And you can see here your source, your client. You see here your server. You see the initial SYN. You see the SYN ACK, and then you see the ACK, and then you see a bunch of communication going, a bunch of ACK back and forth between client and server, right? Okay, cool. Now, but what are these sequence numbers? Now, the sequence numbers will number the communication progress starting up from 0 and increment as more and more data is sent. So that's why the initial SYN was sent for synchronize. So for this session, they could synchronize their counting and then count up from there. Now, what does this indicate? It says here consecutive SYN, no SYN ACK. So you see the client is talking to the server, it has the SYN flag set, and then it happened again, and then it happened again. But the server here never sends the SYN ACK, as you will see here in this packet capture. This is an excerpt from Wireshark again. So what's this indicate? In this case, it indicates the server is not responding. Now, it does not indicate why the server is not responding, because there's a chance the server is not responding because maybe the server never even got it, so it wouldn't respond. But you don't know. The only thing you know for sure is that the server is not responding based on this packet capture. Now, what does MSS indicate? What is MSS? Because if you're looking at the TCP protocol, and sometimes if you look at your packet capture, some information you may see is called here MSS, and you're wondering what that is. Well, MSS actually indicates maximum segment size, and this indicates the maximum size that a TCP can send. It defaults to the IP MTU minus 40, and the default IP MTU on Ethernet is 1500. So as you can see, if it's 1460, then it is actually using the default IP MTU to calculate this maximum segment size here. Exercise 12. How can MSS help in troubleshooting? As we see here, one host here is sending an MSS of 1260 client to the server with the SYN flag set. The server responds with a SYN ACK with a higher MSS value. But so how can this even help us in troubleshooting? Actually, The MSS can indicate that there's a reduced maximum transmission unit for a link. In some cases, it may be possible to send packets that may be too large for a link. If those packets cannot be properly fragmented, they may not ever make it to the other side of the link and may be dropped. From the original intent, the MSS was set by the client. The client will say, hey, here's my MSS. The server will also respond to the client, hey, here's my MSS. So the client says, hey, really don't send me anything bigger than this. The server says, okay, you can't send me anything bigger than this. So by telling the other side what the MSS is, you can actually avoid some fragmentation issues if the MSS is set properly and accounts for the link. Now, learning verification. What does it mean when one says that IP encapsulates TCP? What are the 7 layers of the OSI model? What is the TCP three-way handshake? Can an application work if the TCP three-way handshake fails? What do SYN and ACK mean? What are sequence numbers? What do consecutive SYN without a SYN ACK represent? What is MSS? What can be indicated by an MSS less than 1460? TCP is encapsulated by IP because an IP header precedes a TCP header. As you know previously, we showed a diagram showing that data encapsulation. It's viewable on prior slides. Now, IP is encapsulated by layer 2 because a layer 2 header precedes an IP header. Now, this is about the OSI model, and here are some handy acronyms you may use to remember the OSI model. My personal favorite is all people should try networking data packets. Now, a TCP application cannot work if the TCP handshake fails. SYN is referring to synchronized sequence numbers. It's seen on initial packets from a host. ACK equals acknowledgement, signals to other side what has not yet been received. Sequence numbers number the communication progress, starting up from 0 and incrementing as more and more data is sent. Consecutive SYNs without a SYN ACK will indicate that the server is not responding. MSS indicates maximum segment size, the maximum size that TCP can send in a single segment. MSS defaults to the IP MTU minus 40. Since the default IP MTU on Ethernet equals 1500, the MSS is usually 1460. If the MSS is less than 1460, it usually indicates that something is decreasing the MSS and or MTU. For example, if tunneling is being used, the additional tunneling headers can reduce your usable MTU. This concludes the lesson on Transmission Control Protocol, TCP. Thank you very much.